Hello everyone, this is problem set 3, problem 5. A cylinder contains 0.1 moles of an ideal monatomic gas. Initially, the gas is at 1 times 10 to the 5th pascals and occupies a volume of 2.5 times 10 to the negative 3 cubic meters. For part A, find the initial temperature of the gas in kelvins. Okay, so I'll just write down the given information that I have. And that is that the number of moles is equal to 0.100 moles. Okay. I know I'm dealing with an ideal monatomic gas. Given that my initial pressure is at 1 times 10 to the 5th pascals. And that my initial volume is 2.5 times 10 to the negative 3 cubic meters. All right. And so for part A, I want to find my initial temperature of the gas in kelvins. Okay. By the way, the stuff I have here in the blue ink, these are unit conversions that I want to have in my cheat sheet for exams or homeworks. So I just write them here in case you guys think it might be useful for you as well. All right. Okay, so finding my initial temperature. I know that the ideal gas law, PV equals nRT, right? And I am given for the initial state, I am looking for my T1. This is what I need, right? R is a constant, I know that. N was given to me right here. V was also given to me right here. That's V1. And P1 was also given to me right here. Therefore, I can solve for T1, right? So P1 V1 equals NR T1. And that's just using the ideal gas law for the first state in state 1, initial state. Okay, so let's plug in our knowns. P1 is 1.00 times 10 to the 5th pascal, right? Initial volume, 2.50 times 10 to the negative 3 cubic meters. And that's equal to the number of moles that was also given as 0.1 moles. And R, I'm going to choose between this version of R or this version of R. I'm going to choose the first version right here because I want to convert the joules into kilograms meter squared over second squared so that I could cancel units out. All right. So anyways, I'm going to choose 8.31 joules per mole times Kelvin. And I'm looking for T1, right? So I have everything except for T1, which is what I'm looking for. So I'll just do algebra, shuffle stuff around, and solve for T1. Okay, so this becomes T1 will be equal to 1, my pressure, 1 times 10 to the 5th. Instead of pascals, I'm going to convert that to kilograms over meters times second squared times my initial volume, which is 2.50 times 10 to the negative 3 cubic meters. And then divide that by the number of moles, which is 0.1 moles. And for my R constant right here, instead of the unit in joules, I'm going to convert it to kilograms meter squared over second squared, right? So times 8.31 kilogram meter squared over second squared, Also, I won't forget my units of moles times Kelvin in the denominator. So times mole times Kelvin. And then I could cancel out units and plug it in my calculator, and I will find that my initial temperature is equal to 300.84 Kelvin. Okay? That is my answer for part A. All right. For part B, if the gas is allowed to expand to twice the initial volume, so the final volume, V2, is equal to twice the initial volume, or 2V1. All right, first I have to find my temperature, my final temperature, or sorry, let's call that T2, and also my final pressure, so P2. All right, and there's three scenarios for an isothermal scenario, isobaric, and adiabatic. So let's start with the isothermal scenario. Okay, so isothermal, right? And that just means there is no change in temperature. So T1 would be equal to T2, which is a constant, and let's just call that T. Right? So right away, I already know I can solve for this, T2, without even trying, just because I know that T1 equals T2. It's isothermal. So T2 is equal to T1, which is equal to 300.84 Kelvin. That's what we solved for in part A. All right. And for the final pressure in an isothermal process, let's look back at our handy-dandy ideal gas law. PV equals nRT. Okay? What are constants here for isothermal? We know T is a constant, right? Because T1 equals T2. So this is a constant. R, that's a gas constant. We know the value of that. And N was also given to us, and that's also a constant. So for the initial scenario, if these are constants, right? If these are constants, let's say that the initial scenario we have P1 and V1 equals some constant. In the final scenario, we have P2 times V2 equals that same constant. So as a result, therefore, for an isothermal process, P1 V1 would equal P2 V2, which is just equal to the constant nRT, right? Okay, now that we know this, let's solve for the P2. Okay, let me just erase this because I like to have clean notes. Okay, so first of all, what is P1? It's given to us. 1 times 10 to the 5th Pascal. So 1.00 times 10 to the 5th Pascal. And then V1, the volume, it wasn't given to us. We just know that, it was given to us right here, right? Okay, but also I know that V2 is just equal to 2V1, right? So let's plug in V1, 2.50 times 10 to the minus 3. So 2.50 times 10 to the minus 3 cubic meters is equal to our final pressure times V2, which is twice V1, right? That was given. And what is twice of V1? That would just be 5 times 10 to the minus 3 cubic meters. Okay, so I have everything and I can solve for P2. Plug that in my calculator and cancel out my units. I would get that for an isothermal process, P2 is equal to 50,000 pascals. Okay. So I was able to solve for my final temperature and final pressure for an isothermal process. Moving on to the second scenario, that was isobaric right here. Okay. So isobaric process. And we know that for an isobaric process, that means we have constant pressure. So P1 would equal to P2, right? And so it's, again, we're solving for T2 and P2, the final temperature and final pressure. Right away, I already know my final pressure. Final pressure is equal to P1, which was given to us. So P2 is also equal to 1.00 times 10 to the 5th pascals. Didn't even have to solve anything. I just know in an isobaric process, pressure is constant. So P1, initial pressure equals final pressure. Okay, and for T2, in an isobaric process, in order to find this, let's use again the handy-dandy ideal gas law. So PV equals nRT. And this time, what is constant for an isobaric process? Pressure, the moles, and the constant R. Oops. So as a result of that, for an isobaric process, V over T, the initial volume and initial temperature is equal to the final volume over the final temperature. Okay? Right? Because I'll just show why that is. Because V over T is equal to the constant nR over P. And these are all constant. See? Constant, constant, constant. Okay? So let's plug in our known values. It was given that our volume, initial volume, is 2.50 times 10 to the minus 3 cubic meters. Okay, our initial temperature was solved for in part A. That's 300.84 Kelvin. Okay, is equal to the final volume, which we said was equal to twice the initial volume that was given to us. So 5 times 10 to the minus 3 cubic meters. And that over the final temperature. All right, so we have everything, all our values except for T2, so we can solve for T2, right? Cancel out the units, we would get T2 is equal to 601.68 Kelvin. Okay. And we knew our initial, or our final process just because it's isobaric and pressure is constant. Okay, moving on to the third scenario, which was adiabatic. Okay. Adiabatic, right? So we are looking for our final pressure and final temperature, right? Unfortunately, nothing really cancels out in adiabatic process, because if we look at our, this time not so handy-dandy ideal gas law, PV equals nRT, what is constant? Just the moles and R. Because in an adiabatic process, the pressure, changes, the volume changes, and temperature changes. So I'm not really going to use the ideal gas law for the adiabatic process this time, unfortunately. However, I do know that we are dealing with a ideal monatomic gas, right? And when we're dealing with an ideal monatomic gas, actually, when we're dealing with an adiabatic process for ideal gas, we have two formulas that we should have in our cheat sheet. And that is that initial pressure times initial volume to the power of gamma, which is the ratio of molar heat capacity, is equal to the final pressure times the final volume to the power of gamma. Okay? And the other, so that's the first equation we should have in our cheat sheet. And the second equation we should have is initial temperature times initial volume to the power of gamma minus 1 is equal to the final temperature times the final volume to the power of gamma minus 1. All right, and these two equations you can use for an adiabatic process, for adiabatic process for an ideal gas. Okay. All right, so let's first find our final pressure by using this first equation. So P1 V1 gamma equals P2 V2 gamma. All right, it was given to us in the problem that our initial pressure is 1.00 times 10 to the 5th pascals. All right. It was also given to us that we were also given our initial volume, but because I know that I'm working with these equations, and eventually I'm going to have to go V1 divided by V2, V1 to the power of gamma divided by V2 to the power of gamma. I'm not even going to use this number, this value. All I'm going to do is I know that V2 is equal to twice of V1, and that's all I'm going to use, okay? Just to save myself some time. So V1 to the power of gamma. Oh, what's the other thing I should know? What is gamma? Okay, remember our values for gamma for different types of gases? That is, so gamma, the value of ratio of heat capacity for different types of gases. I'll write that here on the side. So gamma equals 1.67 for a monatomic gas, which is what we have in this scenario. It's equal to 1.4 for a diatomic gas. And it's equal to 1.3 for a polyatomic gas. Okay. In this scenario, again, we are dealing with ideal monatomic gas. So our value for gamma is 1.67. Okay, so I'll plug that in here. So V1 to the power of why is this in blue? The power of 1.67 is equal to P2, which I'm looking for, times V2, which is just twice 2V1, right? Twice of V1 to 1.67 to the power of 1.67. Okay, so I'll just solve for P2, which is going to equal to 1.00 times 10 to the 5th pascals. And then I have V1 over 2V1 to the power of 1.67, right? And we'll see that the V1s cancel out. So I have P2 is equal to 1 times 10 to the 5th Pascal multiplied by 1 over 2, or 1/2 to the power of 1.67. And if I plug that in the calculator, I would find that my final pressure for an adiabatic process will equal 31.425 times 10 to the 3rd pascals. Okay, that is my final pressure. Okay. Now I will use the second equation to find my final temperature. So T1 V1 gamma minus 1 is equal to T2 V2 gamma minus 1. All right. And in part A, we solve for our initial temperature right here. So I know that it's 300.84 Kelvin. Again, I'm not going to substitute the value for V1 because I just know that V2 is equal to twice V1. So V1 to the power of 1.67, which is my gamma, right? That's my value for gamma, minus 1 is equal to T2, which is what I'm looking for, times final volume to the power of gamma 1.67 minus 1. Okay? So then T2 will be equal to 300.84 Kelvin times V1 over V, or not V1 over V2, but V1 over 2V2, because V2 is equal to 2V1. So V1 over 2V1, right? Because V2 is twice the volume of the initial volume. And then to the power of 1.67 minus 1, or 0.67. Okay, and again, my V1s cancel out, so I have 300.84 Kelvin times 0.5 to the power of 0.67. So my final temperature, if I plug that in the calculator, will equal to 189.08 Kelvin. And that is my final temperature for an adiabatic process. Okay, hope this helped.